So at this moment, I'd like to call upon Mr. Mainak Sen up onto the stage to make his presentation. Mainak has 2 decades of experience in analytics, research, and technology in global companies spread across India and USA like Infosys, Thermax, Dhaka Research. He leads the analytics practice of Business Brio as director and has keen interest and vital experience in statistical mathematical models applied to technology, industry, business, and economics. Moina completed his MBA from Michigan State University and BE in Production Engineering from Jadavpur University. He is also actively mentoring aspiring data scientists.
Good afternoon. I guess this is the last session before lunch, so I won't keep you too long. And the other thing is, given that I'm here with Business Brio, unlike the previous speakers, I do not focus on any particular vertical. So it's not banking or media. And as I was thinking of what to talk about, so I thought that maybe we will focus, I will speak briefly about some technique, which kind of is, as far as I am concerned, industrial applications, it's kind of in the frontier right now. Maybe not as popular as standard machine learning techniques are, like standard classifiers or supervised and unsupervised learning. So what I'm going to talk about briefly is reinforcement learning. So probably some of you, I hope, have heard about it. It's a different learning paradigm from supervised and unsupervised learning. And I personally feel that it has a huge potential going forward in the domain of business analytics and applications to business and industrial problems, particularly with Industry 4.0 coming up, and also in some of the applications that we heard about, for example, in media and banking. So this is one example of, it was in the news a couple of years back. I don't know how many of you have heard about it. So there's a game called Go. How many of you know Go? So there's a game called Go, which is supposed to be much more complex than chess. So we all know when we were in college, there was this big match between Kasparov and Deep Blue and Deep Thought, I think. And Deep Blue defeated Kasparov, and there was a big furor about that, right? Everybody was talking about it. Now that was about 15, 20 years back, if my memory serves me correct. Now, in 15, 18 years since then, nobody actually came close, forget about beating, came close to, no computer system came close to defeating or playing with a human Go player of any competency, forget about world champions. The technical reason for that is something called game complexity. So Go is a far more complicated game than chess, so to put it simply. And so it was beyond the pale. I mean, it was beyond what was capable. And then suddenly in around 2000, I think this was 2016, right, there was this company, Google Brain or Deep Brain, and they came up with AlphaGo, and they defeated the running world champion of Go in 4-1. So this algorithm defeated the running world champion in Go 4-1. So this was a huge deal because this was something completely out of the blue. It was not foreseeable at that point in time, and then they came up with this. And what they did was, actually that was an implementation of something called uh, deep neural network, which implemented reinforcement learning. So I'm just going to talk about briefly what reinforcement learning is, and obviously this is a great achievement, but we are not really that much interested in playing video games or games. We are more interested in real applications where business can use it or government can use it, and what are some of the areas where this can be implemented or used. Just to give an introduction, what reinforcement learning is all about is, as we know that we have supervised learning and unsupervised learning, and that has been around for a long time, and most of the algorithms that we currently use in a mass scale are either supervised or unsupervised, and there is a little bit of what is called semi-supervised. But reinforcement learning is actually something which is very highly suited for what are known as temporal data. So, for example, data which is coming sequentially. So, sequential data or sequential decision making problems which are very relevant in any kind of business process. So, if you think about, typically you are thinking about, let's say, managing a stock, right, or managing an investment portfolio. So, if you are managing an investment portfolio, it's not a one-time decision, right? You do not just buy one stock or sell one stock one time. You kind of maintain you buy something, then you sell something, and then you buy something else. And your goal is to kind of maximize your reward over a longer horizon, right? So, that kind of sequential problem, which is very common, is what reinforcement learning tries to address. And this is implemented through neural nets to a large extent nowadays. So, what we have here is that we have a software agent which makes observations and takes actions within the environment, and in return it receives rewards. So, the rewards can be tangible rewards like money, or the rewards can be some goals to be achieved, right. And so, the objective is to learn to act in a way that maximizes expected long term rewards. Now, this is what is different from your standard supervised learning or unsupervised learning. Typically what you have, think of it this way. I'm trying to give you a real example of where this can be applied. So, for example, all of us are probably familiar with something like churn analysis, right. So, you have a customer, and you have a history, you have transaction history, and you try to find out whether this particular customer is likely to switch out of your business and go to your competitor or go to somewhere else, right. So, that's a very old classic problem. That is the domain of supervised learning. But on the other hand, what reinforcement learning, the kind of problems it is addressing is, okay, so you know that some customers are at higher risk of leaving your business, of churning, right. What kind of incentives can you give that customer to lure him back or retain him in your business, right? And that might not be just one thing, right? It can be a number of promotions, it can be a number of interactions, right? It can be different offerings. So, that is something which has to be a policy. So, what reinforcement learning helps you to do is to come up with optimal policies, correct, so that you can maximize your gains or maximize your rewards over a longer horizon, right. So, that is the kind of application that this is useful for. So, you basically have an agent which takes action, and the environment generates some observations and rewards for the agent, and this cycle goes on. So, these are some of the possible business examples. So, you have, for example, I was talking about industry 4.0, right. So, you have controlling of any process plant. It can be a power plant, it can be a cement plant, it can be any process industry, right, where the entire process flow can be optimized, right, based on something like this. Humanoid robots, right? Again, in manufacturing, you can have robots which learn to pick up things, for example, or actually walk or do some sophisticated maneuvers, and the robot actually learns what to do, what is the best way to move around in a shop floor, for example. Manage investment portfolio that I talked about. Digital marketing, so for example, online banner ads, right? What ads do you show to a person, correct? And there is typically a trade-off. You can either keep showing the same ads, correct, and get a fixed reward, right? But the other option is to you explore some different ads and see how that response is going to be, right? You do not know whether that new ad is going to generate more revenue or more click-throughs than the old one, but this is typically what we are going to talk about right at the end. This is an example of what is called an exploration versus an exploitation trade-off, right? So you have, when you are learning in a longer horizon, you typically try to balance these two things. You explore new things, just like human beings. You try to explore new things, but at the same time, you also try to exploit the knowledge that you already have, correct? So you do not want to sacrifice too much of your present cost or your present rewards for the future gains. So you do try to do some kind of discounting of the future returns and balance it. So that is another kind of application that this is actually, so online banner ads, exploration, exploitation strategies are actually being implemented. That's already done. Investment portfolio is something kind of, it's still in the frontier. I do not know of any real success stories on this, but probably in the next few years it will come up. So the key distinctions is that there are no supervisors, only a reward signal. So that's how it is different from supervised learning. You have delayed and non-instantaneous feedback. So you get feedback, you get rewards, but that typically does not happen today, right? So once you give some incentives to your customer, that customer may stay back, may not stay back, but you will come to know about the decision only in the future, right? So you do not have an instantaneous feedback. It's kind of up there in the future. And the critical thing is that this is applicable for non-IID data, right? So this is not your cross-sectional data. So you are talking about temporal data here, right? So your temporal data, sequential data, so sequential action is important. So rewards are, so these are just defining some of the terms. Now, I think, yes, 2 minutes? Okay. So basically the select actions to maximize total future reward, that is what your end objective is. You have a horizon and you try to maximize your rewards over that entire horizon, doing some kind of discounting. So I will spare you the details. Anyway, I have just 2 minutes. Now these are some technical details that we'll skip through quickly. Now what I just want to focus in this one before I end, that these are some of the key components of an RL agent. So you have a policy, which is an agent's behavior. So an agent's behavior function. So how, as I said, that depending on the state, what is the action that the agent chooses, right? So that is the policy, and you try to optimize that policy. And the value function is how good is each state given its action, right? So if because we are talking about sequential decisions, at each point in time, the state of the system changes, correct? So whether the system is good or bad or it is better, right, you have to somehow quantify that. So that is what the value function is. And then you have a model which represents the environment. So these are typically the different kinds of RL agents that are there. We have value-based agents, policy-based agents, and actor-critic agents. So this is kind of the different kinds of taxonomy that you have for RL agents. So you have policy and value function based agents and the actor-critic agents right at the center. as you see. And this is the approach to sequential decision making. The environment is initially unknown, so you do not know the initial environment completely. The agent interacts with the environment and finds out, so it's trying to mimic, you know, the human learning process. The agent improves its policy by doing, it's kind of basically trial and error, and it's like learning by trial and error and discovered a good policy. So what works and what doesn't work, you discover. The software discovers what is working and what is not working, correct, given a long-term horizon, correct. And as I was saying, that a key feature of this is this trade-off between exploration and exploitation. So you explore new opportunities and also you exploit what is already been learned. So those of you who are interested, so these are some of the techniques that are employed. So you know, this last one, the deep Q learning, that actually is the algorithm that was used in that AlphaGo agent, which actually defeated the world champion. And these are actually finding applications in industry right now, for example, mostly in robotics. I would end by citing a few things, few links. So there are, this is a very emerging field, and lot of stuff is coming up every day. So there are excellent resources over the internet that you can refer to, some of which I have cited here, and in fact, most of my slides are from are made from these sources. So with that, I will end because I have run out of time. So if you have any questions, please feel free. Pardon me? Okay, so if you have any questions, yes. I'm sorry I had to rush because of lack of time, but.
Hi, so my question is about the multi-armed bandit problem. So in that problem is basically you adhere to the exploration versus exploitation trade-off. You sit in a casino and you don't know, yeah. So how is that related to reinforcement?
Bandit is actually one of the, so there is something called a Markov decision process, which I kind of hurried through, correct? So the underlying model is something called Markov decision process, which basically tries to say that what happens in the future, correct, depends only on the present, given that so it is independent of the past given the present, right. So MDP, so that is called the MDP, and that is one of the fundamental assumptions of reinforcement learning, a large class of reinforcement learning problems. So bandits, multi-armed bandits is one particular case of a general class of agents called bandits. So bandits is actually one instance of reinforcement learning. You can implement reinforcement learning to a bandit problem.
Hi, here. So I have a question regarding the amount of training data required for
huge. That is another. That's the reason.
Yes, because for supervised and for reinforcement learning, is there a huge difference, like you were saying?
Yes, big difference, and you know, the parameter space for reinforcement learning is also much larger. So that is one reason that why this is, as I said, that this is right up there in the frontier right now. So this is not as popular or as commonly used as your standard algorithms, because one of the reasons is that it needs a lot of learning and lot of bandwidth. So it's the parameter space is huge. So optimization in that huge parameter space is very costly in terms of cycle time.
Okay.
Okay, I guess that would be it. Thanks a lot for everybody.
Mr. Sen, please stay back for your felicitation. I'd like to call upon Mr. Nirupam Chaudhary to hand over the felicitation to Shri Mainak Sen.